The goals are shown here. The key goal we're going to accomplish here is we're going to determine the change in entropy for a chemical reaction under any conditions and see how we can get that from the thermodynamic data table. We'll see this is very nicely related to what will become our equilibrium constant. Now, the first just reminder here, partial pressures are important at this part of the class where we have potentially X and Y as different gases that might react with each other or convert into each other. You can always apply the ideal gas law to each gas separately, so the partial pressure of X times the volume of X, the volume is always the same volume here for the entire, it's always the same total volume here, but the partial pressure of X is proportional to the moles of X, the partial pressure of Y is proportional to the moles of Y, the total pressure is just the partial pressure of X plus the partial pressure of Y. This is a good assumption for ideal gases, and the assumption works really well for non-ideal gases too. So yeah, partial pressures are really important. Okay, next we have a little bit of a derivation. We've only dealt with gases so far, but solutions are where we do a lot of our chemistry, and so it's useful to have the ideal solution model. It's defined sort of by analogy to an ideal gas, and a nice way to understand what the ideal solution model is to have a grid model. So the idea here is that, let's say we have a substance X that's aqueous. That's our solute. Our solvent in this model is just the blank squares. So if the solvent is water, all these blank squares are occupied by water molecules. There's some total volume of our solution, V, and let's say this is an initial volume, V1. Now let's say we do a dilution, so we add some more water to the solution and we go from having a volume V1 to V2. Let's think about what happens to the microstates for each particle, and therefore what happens to delta S when we go from this initial state with a volume V1 to some new state with a larger volume V2. Maybe as a first pass at it, let's assume that it's this exact scenario here where there's two X's, and we can see here we started with 15 grid squares and now we have 30 grid squares here. In this case, what would happen, I can actually just use my rules of probability. My total microstates here is that I would have 15 ways to put the first molecule X times 14 places to put the second molecule X, divided by here, I have two X's, so there would be, if it doesn't matter if I put the first one here and the second one here, or the first one here and the second one there, I'd have to divide by 2, and that would be my initial ways. This is the total ways for the entire system. Similarly here, the total microstates for my entire system would be equal to 30 times 29 over 2. Okay, in this case, when we do this, we get basically a factor of 4 increase in the microstates for our system. That's going to cause a corresponding ln4 sort of change in the entropy. And that's because each individual particle here basically doubled its available microstates, and so that's then what happened to the overall number of macrostates, and then therefore also the entropy. So our idea here is, let's say, assume solution is very dilute. In that case, it's not going to matter here that I go from having 15 grid squares for the first to 14 for the second to 13 for the third. The idea is that I basically just always have the same number of available grid squares for all of them, right? If this were, in fact, in a real dilute solution, maybe I had 10 to the 6 available spots for the first particle, and then 10 to the 6 minus 1 for the second. It's a pretty good assumption that this is also still 10 to the 6. In this case, then, all that's going to matter here is that we'll say that the microstates per particle, little w, is proportional to the volume. Now we can then use this and apply this equation. Delta S is R. This is molar entropy, is R ln microstates of some final state over microstates of some initial state. Little w is microstates per particle. Since we're assuming the microstates is proportional to volume, this gives us this relationship that delta S is nR ln Vf over Vi. So sort of a short derivation, but very, very important here, that when we increase the volume, the main effect is that we get more microstates for each of the solute particles in our solution, and that causes this systematic increase in entropy. So that equation is on our equation sheet right here. Delta S is nR ln V2 over V1, which applies to an ideal gas or ideal solution. If we switch from volume to partial pressure, we can do that using proportions. The partial pressure is proportional to 1 over the volume. And the concentration, if we look at it, is also proportional to 1 over the volume. If I double the volume, my concentration cuts in half. If I double the concentration, that would be equivalent to, cutting my volume in half. So the exact same way here that I switched this equation around and said that V2 over V1, right? The idea here is that V2 over V1 is equal to P2 over P1 to the minus 1 is equal to X2 over X1 to the minus 1. When I plug that into this equation, the negative 1 power, because I'm taking the ln of it, comes out as a negative sign. So I get this form of the equation, which is another nice way to describe it. Okay, so we're going to use what we just derived here to get a very, very important result for chemical reactions. We're going to, for a chemical reaction, look at what is the change in entropy of the reaction under any reaction conditions, not just the standard conditions that we can actually look up right from our table. So if we're at a pressure concentration that's different from the standard value, which is 1 bar partial pressure or 1 molar or 1 molal concentration, the configurational entropy will cause a large change in the entropy change of the reaction. So let's say we have, as an example, a reaction like this, where A moles of A aqueous react with B moles of B solid to form C moles of C liquid and D moles of D gas. From the thermodynamic data tables at standard conditions, we can look up the change in entropy of this reaction at standard conditions. Notice the circle. 298 is where they're normally tabulated. The book will represent this as like delta R S naught 298, or some, I just put it in parentheses here, but either way, you can do that just looking up the values from the table. But if we want to look at some other reaction conditions, we need to know, okay, how does the entropy of my substance, my gas D here, change if we put it at some arbitrary partial pressure D, piece of D, and how does the entropy of my aqueous substance A change if I go to some arbitrary concentration A, which could be 10 molar or 0.01 molar, whatever it is. In general, the applied pressure has little effect on solid and liquid phases, so we're just going to assume that the entropy of B and the entropy of C are just equal to their standard values. We'll justify that a little bit later. It might be useful to think about what we're doing here as a cycle, right? So delta RS is, we're going to be at some concentration of A that's, unknown, just concentration of A, and some partial pressure of the gas D that's, just PD, some unknown. That's delta RS, right? This is under any conditions for any molarity and any partial pressure. We can think about that as the sum of a couple different steps, right? First, we can take reactants and go from the concentration of A back to 1 molar. Maybe I'll call that delta S. Then the middle step here, we go from A at 1 molar to products at 1 bar. That's delta RS naught, just based on the definition of the standard state. Then I'll call this step 3, say, delta S3. I take my products from a partial pressure of D of 1 bar back to some arbitrary partial pressure PD. Okay, so if we again add up all those steps, 1 plus 2 plus 3, this is the exact same process as going from reactants to products under the conditions we're interested in. So delta RS is, step 1 plus the standard conditions S plus step 3. We should be able to find delta RS is delta RS naught minus R ln Q, where Q is your reaction quotient from general chemistry. Products to their coefficients over reactants to their coefficients, and Q is, in this case, the partial pressure of P sub D to the power D. This is a small d, the coefficient, if we go back to our equation here. Little d is the coefficient there. Divided by a to the power of a. So take a minute, see if you can get, right, what is delta S1, what is delta S3? Try to add them up and get to this final answer. In class, we'll sort of walk through the rest of the derivation here, see if you can do it, and otherwise we'll spend a few minutes in class finishing that derivation. Okay, assuming you have derived the answer from the previous set of slides here, that delta RS is delta RS at standard conditions minus R ln Q for the reaction. Now let's use that to calculate all the sort of changes in appropriate thermodynamic variables during a chemical reaction here. So take a few minutes to try to see what you can do with this. What is delta H? What is delta S? What is delta S surroundings and delta S universe? Yeah, go through that as best you can, and then I'll show the answer next. Okay, so the first step here is to think about the reaction. Anytime we're doing this, this is evaporation, but again, it doesn't really matter. Anytime we can write a reaction, we want to do that for sort of a chemical process, in this case evaporating, so liquid to gas for water. We actually calculated delta RH naught and delta RS naught on the previous set of notes, 44 kilojoules and 118.8 joules per mole Kelvin. This would be per mole here as well. Again, so I'll leave one more little gap here. See if from this given information you can calculate delta H, delta S, all of those parameters as best you can. Okay, the first thing to identify here is that we're in sort of the normal chemistry and biology situation where we're at constant pressure and there's no non-mechanical work. So const P with the little star next to it. As we denote on our equation sheet, that means that we can say delta H is Q plus work non-mechanical, and we get back to the very familiar general chemistry. Delta H is just equal to Q. Very useful result to have here. Okay, delta S, so that's what delta H is going to be. It's going to be equal to the heat released. To actually find delta H, the idea here is that this delta H is going to be caused by our reaction. Delta H is extrinsic, so because we're going to convert 2 moles of liquid to gas, the delta H here is going to be equal to 2 moles times 44.0 kilojoules per mole is equal to 88 kilojoules per mole. That's because, remember, this here is per mole of reaction. Since the coefficients here are each 1, if I have 2 moles of water, I need to do 2 times that 44 to double the amount of moles of water that are going to be consumed, and therefore get, 88 with no moles anymore because the moles just canceled out. One important caveat here that I forgot to mention was that this is an ideal gas, or we're assuming water is an ideal gas, so that delta R of H at these conditions, which are not standard conditions, we have PH2O is only 0.01 bar, are just the exact same as the delta H at standard conditions. In general, the enthalpy of normal substances doesn't change very much with the applied pressure. Maybe we could do some counterexamples there, but for ideal systems, like an ideal gas here, this is going to be a good assumption here. So that's the assumption that we're making here, is that delta RH is independent of the partial pressure of water. For delta S, it's going to be the same thing, but we know that delta RS is in fact very highly dependent on the actual reaction conditions. So first we're going to need to do delta RS at these conditions is delta RS naught minus RLNQ, which is going to be my 118.8 joules per mole Kelvin minus 8.314 joules per mole Kelvin times ln Q. In this case, it's always a good thing to write down at the beginning. Q is just going to be the partial pressure of H2O here. Because H2O is a liquid, its entropy doesn't really depend on the partial pressure of anything. So yeah, it's just only the gas here. Only gases in aqueous species show up in the reaction quotient for that reason, because they have this configurational entropy term that we need to keep track of. And again, remember when we plug into Q here, we need to be in units of bar, because the standard state for a substance is 1 bar of applied pressure. So this is Q is technically unitless because it's technically pH2O over 1 bar, adjusting from H2O at the current pressure to the standard pressure. Okay, when I plug in, I get delta RS is here 157.09 joules per mole Kelvin. So this is even more positive change in entropy. That should make sense because the products here have even more entropy at a partial pressure of 0.01 bar than they did at 1 bar. So even bigger increase in entropy here compared to at standard conditions where we'd make the gas at 1 bar of pressure. Again, then we have the exact same term as before. Since we're converting 2 moles of liquid to gas, we have to multiply by 2 here. So 2 moles times 157.09 joules per mole Kelvin. I keep missing my units here, but we'll fix it. Joules per Kelvin there. Okay, now what about this process? Well, the water evaporating, it's a chemical reaction in general. There's no reason to expect this to be a reversible process. In fact, if we think about this process, if we leave the water out in the room, in general, in most rooms, what's going to happen is the water will evaporate and it will never go back down to make a puddle of water on the floor. So we probably expect this to be a spontaneous, irreversible process where the water will evaporate, and it will never sort of come back. Might be what we expect. So yeah, we can't say delta S of the universe is 0 necessarily. I guess in theory it might turn out to be, but in this case we can just calculate delta S of the surroundings here using our normal equation. That's going to be Q sur over T sur, which if we think about it here again, we're going to assume the surroundings stay at equilibrium. That's usually a good assumption. This is negative Q of the system over T of the surroundings. Now we had up above here, I erased it, but we had delta H was equal to Q. So this is going to be negative delta H over T of the surroundings, which is going to be equal to negative 88. Units-wise here, it's useful to go back to joules since my delta S is in joules per Kelvin. So I'm going to go back to joules. So negative 88 times 10 to the 3 joules per, I guess it's just joules there, divided by T sur, which we did this process at 25 Celsius, which is 298.15 Kelvin. When I plug that in, I get negative 295.15 joules per Kelvin. And we find that the overall delta S of the universe, adding them up, is 19 joules per Kelvin. That means this is a irreversible process, and it is a process that actually can occur. The water can evaporate and end up with 2 moles of liquid water vapor at that 0.01 bars of pressure. Again, this general approach is going to work for any sort of chemical reaction. We had this key derivation. The entropy of a substance, especially gases and aqueous species, depends very strongly on the partial pressure, the concentration, and then that's going to really govern what happens to the entropy of the universe during a process. The enthalpy is going to give us information about the entropy change of the surroundings. The entropy change, just the energy levels in my system, is going to give me information about the energy entropy change of my system. And when I add up those two terms, there's sort of the balancing between how does the entropy change in the surroundings, how does the entropy change in the system, to determine whether a process is, reversible, happens both directions, or only happens in one direction, or is, sort of completely impossible.